Hi, this next video will formalise what we mean by probability, give some definitions and some basic theorems. You might have seen these before, but this is going to give everyone a level starting point for our course. When we talk about probability, often people talk about flipping a coin. What's the chance of a head or the chance of a tail? And it's interesting to think about what makes that appear as a random process. If you started out with a giant coin, like this fellow, and tried to flip that, you'd have a fairly good chance of controlling which way up it lands. The process of hoiking it up, tossing it and throwing it. If you want to get a head, you'd probably get a head. If you wanted to get a tail, you'd probably get a tail. If you do the same with a small coin, it's really hard, and it's random effectively. And it's random enough that this is actually, the official way of deciding who starts major sporting tournaments. Here's the World Cup final between France and Croatia in 2018. There's the coin toss. It's the official way of creating a random outcome in these sporting events. Why would it be random? Why would it be so like that when it's not in other circumstances with the bigger coin, or why something else might not be? And you can see where this comes from for certain systems by just taking a look at this particular instance. If you look at this function here, we're going to generate a sequence of numbers which is in the range 0 to 1. We're going to start with some value x0, and we have a simple iteration where the next value in the sequence is equal to the value before multiplied by some number r multiplied by 1 minus the previous value. So it's a pretty simple equation, and you can pick some values and see what happens. So that's the equation at the top, that's the iteration we're following. Our first value is x0 is 0.6, so that's where we start here. This is the number of iterations on the x-axis, so our starting point at 0 iterations is 0.6, and we've picked a value of r of 0.5, so that's the value r there. And we can see what happens to our values of x with each iteration, and in this instance it decays nicely and evenly, and we can see what happens to it at the end. And this is looking like an entirely predictable process. You can tell what's going to happen over time, and that's all good, not very much random about it. If you pick a slightly different number, now r is 3.5, everything else is the same. Just flicking between the two, you see the equation is the same, x0 is the same, it's just our coefficient r that's changed. So it was r 3.5. Now we've got a different response, very different response. It's an oscillating response, and it looks very different, but it's still got a pattern to it. You can see that the period of this oscillation and the signal of the oscillation is looking actually quite constant. So whilst it is not stable at a particular value, we do have a repeating pattern in our response. But if we take it up a bit more, so we still have x as x0 is 0.6, and now r has gone up to 3.9. So before it was 3.5, now it's 3.9. We've got a very different looking response again. So now as n progresses, this response looks really jaggedy, up and down. There's a bit of a pattern maybe, but it looks very unpredictable. It doesn't mean it is unpredictable. If you run this process with these values, every time you'll get this response. So it's a predictable response, not random response, it's a predictable response. It's just a bit crazy. But what makes a process seem random then, in the case of flipping a coin, is when you can just have a tiny change and it completely changes the outcome. So look at this. We're changing the initial value of x1 by less than 1/100 of a percent. So it's a tiny change in x0. R is the same, and you can see a dramatic change in the outcome. So with that small change in x0, now the outcome looks like this. Before it looked like that. So if you're trying to predict what your value of xn is going to be, and you've got a value of r of 3.9 in this case, then the output is going to be very susceptible to any small errors or any small deviations in this value. So we've got a system that has an instability with regard to perturbations, and if you're flipping a coin, that's the type of system you have. The tiniest change in how you're holding the coin, or the weather conditions, or how much you flip it, the force you use, the tiniest change in that will give rise to a system which has very different outcomes, like this system here. And so that generates what is effectively a random process. Small random events then come to dominate what the outcome of that experiment is. And so we have an intuitive sense that randomness exists from experiments like that. And we can see here from an engineering equation point of view how they can actually occur and how some systems are very sensitive to them. So let's define exactly what we mean by a probability then. And the simplest way of defining it is to say that if you have a sample space which consists of a finite number of outcomes and that each is equally likely, then the probability of an event A, so that's probability of A there, is equal to the number of points in A divided by the number of points in S. That's to say the number of points in the event divided by the number of points in the sample space. And remember, each of those events is equally likely. And if that is the case, then that's what we define as the probability. And that gives us some limits. If the event A is everything in the sample space, then the probability of the sample space must be equal to 1. And so, for example, for rolling a fair die, sample space is 1, 2, 3, 4, 5, 6, and our event here is defined as the outcomes 5 and 6. So with that, the probability of getting our event A is equal to the number of points in A, which is 2, 5 and 6, divided by the number of points in our sample space, which is 6, and that's equal to 2 over 6, or 1/3. So here we've got a definition for a probability. Now, a more general definition is a counterpart to relative frequency. We talked about relative frequency in the mini lectures last week when we were looking at an actual physical experiment. And so these ideas tied together, they sort of go in parallel together. Here's F is frequency, rel means relative frequency. So that tells us it's the frequency of A, of our event A, divided by the total number of trials. So this is another way of writing what we did on the previous page, but it's a bit more general. It says that the relative frequency of A is the number of times you get A divided by the number of trials. If A never occurs, then the frequency of A is 0. If A always occurs, then of course the frequency of A is n. And then if you convert that into the relative frequency must be greater or equal to 0, and it must be less than or equal to 1. If the event is the whole sample space, then of course the frequency of that must be n, because it happens every time in our n experiments, and therefore the relative frequency of the sample space is 1. Okay, that's all obvious, but it provides a firm grounding for our understanding. So if we have two events that are mutually exclusive, then that means that the frequency of getting A or B is going to be equal to the frequency of A plus the frequency of B. So we can write then that the relative frequency is going to be true too. The relative frequency of A or B will be equal to the relative frequency of A plus the relative frequency of B. And that's true when they are mutually exclusive, so that the intersection of A and B is 0. So we can have a general definition of probability then. Given a sample space S with each event A of S, there's an associated number, P of A, called the probability of A. And so long as the following axioms are satisfied, then this gives us the probability. So for every event A in S, the probability of A must be between 0 and 1. The probability of the whole sample space must have a value of equal to 1. And for mutually exclusive events A and B, the probability of A or B will be equal to the sum of the probability of A plus the probability of B, so long as they are mutually exclusive. So from those rules we can derive some theorems. The first is about the complement of A. So we saw the complement earlier. The complement is everything within the sample space that's not in A. So the probability of the complement of A must be equal to 1 minus the probability of A. Now this is very useful often because it's sometimes easier to find the probability of something not happening than it is to find the probability of the thing happening. So here's an example of that. If you toss 5 coins simultaneously, we want to find the probability of the event that at least one head turns up. Okay, so that's what we're trying to study. What's the probability that at least one head turns up? Well, we can map out the experiment. We're tossing the coins simultaneously. So this is coin 1, this is coin 2, this is coin 3. These are all the possible events that could take place. 1, 2, 3, 4, 5 coins. Each could be head or tails. They're all tossed at the same time, and so you can see there are 32 possible events in this experiment. There's one of them that has 1, 2, 3, 4, 5 heads, so that would satisfy the test because we're trying to find the event that at least one head turns up. So yes, so that at least one has turned up there, at least one has turned up there, at least one has turned up there. You can see there are many routes to satisfy this event, and there'll be many outcomes inside that event. But it's going to be tiresome to work through each one individually in this manner to find out all of them. There are 32 outcomes in our sample space, but if you think about the complement of our event, the complement of at least one head turns up is that no heads turn up. So the complement is that no heads turn up, and there's only one outcome that satisfies that one there. So it's easy to find how many outcomes are in the complement of the event. So the probability of the complement is 1 divided by 32. There's one outcome that satisfies the complement. There are 32 outcomes in the sample space. So our definition of probability says the probability of a complement is 1 divided by 32. And then we can use our definition of the complement. So the probability of A must be equal to 1 minus the probability of the complement. And so of course that's 31 divided by 32. So the complement's a simple concept, and it's very useful to use when you can identify its use correctly. So theorem 2, additional rule for mutually exclusive events. You've probably seen these before. We're just running through them to make sure everyone has. So we have mutually exclusive events, A1, A2, and so on to AM, and we want to find the union of all of those. So the probability of all of those events happening, if they're mutually exclusive, you add up the individual probabilities of A1 and A2 and so on to AM. So for example, a survey tells us how many cars are visiting a garage per day. And we get a bit of data. There are 10 to 20 cars, 21 to 30 cars, 31 to 40 cars, and so on. We have the probability of each of those occurring as the number of cars that come to a garage each day. And are these mutually exclusive events? Well, I think so. If you had between 10 and 20 cars at your garage that day, it's not also possible to have had 25 cars at the garage that day. So it's not possible that you're in both of these at the same time. So the number of outcomes that are in the same, the number of outcomes that will be in more than one of these events will be equal to 0. So we can answer a question now with this sort of data. What's the probability of at least 21 cars coming in a day? So the probability of at least 21 is the probability of 21 or more, and that's equal to the probability of 21 to 30, along with the probability of 31 to 40, and the probability of 40 or more. And so we can add up each of these individual probabilities then to find the total. And in this case it's 0.72. So that was addition. Theorem 2 was addition for mutually exclusive events. Theorem 3 is addition for arbitrary events. So that doesn't have the condition that they're mutually exclusive. And this is a similar form. Probability of A or B is equal to the probability of A plus the probability of B. And now it's minus the probability of A and B, the intersection of A and B. So obviously the theorem 2, this term was 0, but now we're considering non-zero cases here. So to give you a simple example, throwing a die, what's the probability of getting an odd number that, or a number that is less than 4? So our event is an odd number or a number that is less than 4. And we can find the probabilities of these individually. An odd number, there were 3 out of 6 for that, so that's a probability of a half. Number less than 4, again there are 3 out of 6 ways of getting a number less than 4, so again that's a probability of a half. The probability of A and B, so that's the probability that our outcome is in both A and B, is 2/6 because the outcome 1 is in A and B, it's odd and it's less than 4, and the outcome 3 is also an odd number and less than 4. So the probability of A and B is the probability of getting a 1 or a 3, and that's 2 out of 6. So with that we can work out the probability of getting an A or a B. So the probability of event A or B, which is an odd number or a number less than 4, and that will be equal to a half plus a half minus 2/6, which equals 2/3. Okay, so thanks for listening to that. These general definitions will enable us to carry on with all the other material that we're going to do coming up. Next lecture will look at conditional probability in independent events. It will look at sampling with and without replacement. Thank you very much.